So let's look at the distribution of departures between inter-arrivals. And obviously there are two phenomena going on. You have arrivals and departures. Both I'm going to model as Poisson processes. So in other words, here you have time and things are coming and things are going. So you have two processes. So you can see, I mean, in the way I have written, XTs are the arrivals and YTs are the departures. So in a bank or in an airport, people are coming in randomly. Then either people or airplanes are also going out in randomly. So if you, this is the inter-arrival time. So let me call this to be a random variable. We notice, so let's say this is a Poisson process with the parameter lambda t. And this is Poisson with another parameter, let's say mu t. So lambda and mu, it doesn't have to, or they don't, so different rates. This is the inter-arrival time. So what we are interested is to find the distribution of these departures of y between during this random variable. This random variable represents the inter-arrival time, which is exponential. We have seen this earlier. So during this duration, how many departures are there, provided that both the processes are Poisson. So Poisson means probability of x of t equal to k is e raised to minus lambda t to the power k over k factorial. Similarly for y. So let me call, what we want is what, so let me call this random variable to be n. So n is the number of this is of course a random variable because these departures are also at random times. And the arrivals are at random times. This and this has nothing to do with each other. But all this, the distance between two inter-arrivals or two departures is exponential with respective parameter, etc. So we know that the density function of z is exponential. So this is lambda e raised to minus lambda t. What we are interested in is what is the probability of n equal to k. This is what we want to find out. So I'm going to start with, so we know that if you condition this equal to t, that means if you know that this duration is t, small t, then of course we know that during t, this behaves like a Poisson with parameter lambda. So probability of yt equal to k is e raised to minus mu t to the power k over k factorial. So I'm going to use the conditional distribution first. So conditional distribution of n equal to k is given z equal to t. So if you're given that z equal to t, then this is a fixed, the t is fixed. So during, for conditioned on that, this number of arrivals are of course Poisson with parameter which is equal to this duration which is fixed equal to t. So that will be exactly that expression, e raised to minus mu t to the power k over k factor. Now to get this expression from this we can get rid of the condition. So if I do probability of n equal to k given z equal to t multiplied by FCC dt, and t goes from 0 to infinity, that will give us this. So let me pick this up here. So we have probability, what we are looking for, n equal to k is integral of probability of n equal to k given z equal to t multiplied by this. T from 0 through infinity, because this t could be, this inter-arrival duration could be, is exponential, and so z is of course exponential, with parameter lambda. We have it here. So it's exponential. It could be anywhere from 0 through infinity like this. So now if I substitute all these two expressions and we can simplify this. So this is 0 to infinity e raised to minus lambda t to the e raised to minus mu t to the power k over k factorial lambda e raised to minus lambda t dt. So mu k goes outside, lambda also goes outside. So k factorial goes outside, 0 through infinity. T to the power k e raised to minus lambda plus mu t dt. So I'm going to call this a new variable, like say x. So I'm going to put x equal to lambda plus mu times t. So dx over lambda plus mu will be dt. And t will be, of course, x over lambda plus mu. So I'm going to substitute that here. So this turns out to be lambda mu to the power k over k factorial. This is integral. So when t is 0, x is 0. When t is infinity, x is infinity. Instead of t, I'm going to substitute x over lambda plus mu to the power k e raised to minus x. Instead of dt, it will become dx over lambda plus mu. I'm going to pull the constants outside. So it is exactly this expression. So I have lambda over lambda mu k. Here I have lambda plus mu to the power k. Then I have k factorial. Then I have simply 0 through infinity x to the power k e raised to minus x dx. But this is just the, this is gamma k plus 1, which is k factorial. So this k factorial cancels. And you can write this as in this fashion, because this is actually k plus 1, because you have lambda plus mu to the power k here, then one more lambda. So this is k plus 1 here. So k plus 1, I'm going to put k here, 1 here. If I write it this way, I can write this as in this fashion. So you notice that this is suddenly geometric, because p plus q is 1 and k is 0, 1, 2, 3, etc. Because the number of arrivals could be 0, 1, 2, 3, etc. So we get probability of n equal to k is p q to the power k, which is a geometric random variable, etc., where p is, of course, lambda over lambda plus mu. So that's the result. The inter-arrival departures, the distribution of the departures within any adjacent inter-arrivals is a geometric random variable. And if you can generalize this, similarly it goes the other way. The number of arrivals between the inter-arrival departures is also another geometric random variable. I think the parameters will get, p will become q, q will become p, etc. Now if you start adding the number of departures between n arrivals, that will be the sum of independent geometric, that will be a negative binomial random variable. And so that's the result we wanted to discuss.